Hello, Professor, and everyone. Today I'm going to have my review for the invited presentation from Hongyu 2, and the topic is about ferrofluid, and the ferrofluid is quite interesting, and it's why I choose it. The definition of ferrofluid is the ferromagnetic particles are first surrounded by surfactant to avoid van der Waals force, so they won't gather together and instead they just suspend in carrier fluid. So we can see the pictures we often see that the a couple of just black fluid, and to form that kind of ferrofluid, the order of thermal energy should be bigger than the magnetic energy to form it. They could be in the same order, but the point is thermal energy should be definitely bigger. Now, we're interested in the history of the process, and as the professor told us, in 1965, people used grinded magnetic powder to form the prototype of the ferrofluid, and after people starting to investigating and doing experiments on it, there is a group, the peptidization method performed by Califella and the Ramirez in 1974, used the ammonium to get a robust process, making the ferrofluids into nanoscales. So now we got nanoscale ferrofluids, we can start some fun experiments. My professor, he had two setup. One is DC setup, the other is AC setup. Now we could look at the DC setup first. For DC, the ferrofluid was attracted by a permanent magnet into one side, and they have two cameras to observe it. The ferrofluid are moving towards the magnet, and the tank are filled with glycerin. We know glycerin has a very high viscosity, means the camera will always capture the terminal velocity, terminal motion of the ferrofluid. The ferrofluid was once in a circle shape. After attracted by permanent magnet, we can use a dipole model to describe it. There's a lot of math, and I'm not going to do the math here because I only got 5 minutes. But by these fun facts, they can well describe this motion by this dipole model, and they even developed it into some application. We can use some equations to derive our ferrofluid model into the partial h of h in x partial by x divided by partial x, and we can also use the Gaussian meter to get the same graph, and the B graph is the difference of it from the equation and the real measurement. So in this kind of small errors, the ferrofluid model can do a good mapping and can be used as application, which is interesting. Or the other setup, the AC setup, using Helmholtz solenoid to create AC magnetic field. The ferrofluid was dropped at the top of the sink, and it first stretched back and forth, and at the end, it finally turns into rotational modes. The fun fact is the back and forth of the ferrofluid can actually be considered as a current. Then we can study the transverse magnetization, like we just observing the phase lag, and it's also interesting. So in this presentation, I have learned a lot of experiments that we can do with ferrofluids that I never think about it Although the math of ferrofluids, in fact, is pretty hard, but professors have some simple model to make it very easy and clear for all of us, and it is a big contribution to this field. So I like this presentation, and thank you all for listening to my review.